What's up, everyone? It's your boy Orion. We're back at it again. Today, we're going to be going over some projectile motion in kinematics. So, oftentimes, you'll have a problem, maybe something goofy where there's a cannonball shot out of a cannon, or something like that. Um, and essentially, um, it's shot out at a velocity of, let's call this VI. And it's at angle theta parallel to the ground. And you could be given, let's say we're at the edge of a cliff, which is a certain distance or height h. Um, and what they're asking for a lot of the times, they can ask for the time that it takes for the cannonball to hit the ground. They can ask for the um, the final velocity. Um, in They could ask for the component of the y direction or the x direction, or they could ask for just the final velocity, which is um, a different answer in and of itself. And they could also ask for the distance traveled. So there's a lot, and it would be in the x direction. So there's a lot of things that we can go off of just based on our two givens, um, which is our initial velocity and our theta. We can do so much with our kinematics equations. So in this instance, it would be wise to break down um, in physics, a lot of the times when we have a force or a motion at an angle, it's good to break it down into different components. So we could call this Vix, or the initial velocity in the x direction. Um, and we can call this mo direction the initial velocity in the y direction, or VIY. Now, when something is typically in basic university or high school level classes, our VIX, our velocity in the x direction, is going to be constant. And so we don't even have to write an initial or a final if it just stays the same. So we could just call this Vx. Let me get an eraser and erase this. So this is our Vx, and it's constant over time. But with our VIY, with our velocity in the y direction, it's going to change. Why? Because we have acceleration due to gravity pointing in the downward direction. This is going to cause the ball to kind of come up for a little bit, peak, and then start its descent down. And typically with motion like this, we describe it in kind of a parabolic shape. Um, and so we're not really going to focus on forces or anything like that. The only force that's acting on it is the force of gravity. If we ignore air resistance and friction and um, other things like that. So we're given our initial velocity in theta and acceleration due to gravity, which is negative 9.81 meters per second per second. That's our units for acceleration. Okay, now what do we do from here? Let me move this off to the side. What do we do from here? What's our next step? Well, we can use our kinematics equations to find things. So in this instance, let's start with time. A lot of the times they'll have these ugly two-part questions, um, and they will be looking for um, time in the first part and then the final velocity in the second part. So let's start with time. Now, the only thing that's really going to put us on a time crunch is our um, velocity in the y direction. Now, our velocity in the y direction changes over time. It starts off pretty strong. If we draw a graph for it, um, we start off pretty strong, but over time, the velocity decreases until a point where it's at zero. At the very top, our velocity in the y direction is going to be zero. But our velocity in the x direction is going to be the same as how it started. And as we go from there, as we descend, our velocity is going to be negative and increasingly negative because 9 point our acceleration due to gravity is negative 9.81, and it's a negative value. And so as we go on, it's going to be decreasing, and our velocity is going to be decreasing over time until it hits the floor. So, oh, I also forgot. Usually in our givens is also h as well. It would be pretty hard to determine how long it takes to hit the floor if you don't have h or your height. So we're also given this is back to our graph. This is our velocity versus time graph. And right here in this parabolic shape, we have um, our distance versus time graph. Now it would look different in the x direction and the y direction. This is using both dimensions. But in the y direction, it would follow this parabolic shape in terms of distance. It makes sense. And our acceleration versus time graph is also going to be the same. It's going to be negative 9.81. Hopefully that makes sense, and these graphs are a good way to visualize what's going on here in terms of acceleration and velocity and distance and everything. So we can start out with our kinematic equations. Um, we have, let's write it out like this. Um, Distance and the y. Let's start out with our y direction because that's how we're going to get our time and derive that. dy is equal to um, our initial distance, um, which is actually our h, our height. That's where the cannonball started from, plus um, plus our initial velocity in the y direction um, times t, which is our time, plus 1/2 acceleration t squared. This should look familiar. Um, and so our distance, we can subtract our, let me do this. We can subtract our dy by dyi to simplify the equation a little bit. And this is actually going to be our h, or the distance that we traveled. Think about it logistically. You start out at a certain distance, and then this is going to be the distance that traveled. So we travel, this number is negative. We travel a negative version of h. So essentially we can simplify um, this to be h, and then our dy, our distance that we end up traveling, we travel from h to 0, so it's just h. So we can write it like this. Negative h um, is equal to um, the initial velocity in the y direction and plus times t. Don't forget about that. That's important. Um, Times t plus, let me distinguish my t a little bit more. There we go. Plus 1/2 gt squared. This is our kinematic equation that we're going to use to derive this. So, um, how do we get Vx and Vy in terms of Vi, our initial velocity? That's essentially what we're given. We can write them as trigonometric equations. Vx equals cosine theta Vi. Cosine theta in math typically represents the x quantity of something. Now, to do this, to check ourselves, we can draw a little triangle. We have our VI right here. We have our angle theta, which it's launched. And then we have the y direction and the x direction. Now think about it logistically. our x is our adjacent and our vi is our hypotenuse. So we get something v vx equals, sorry, over vi, our hypotenuse, remember SOHCAHTOA, equals cosine theta. So we multiply both sides by vi, and we have our new equation, which is vx in terms of our initial velocity. Now this is awesome. Now we are cooking with chicken here. So we have our Vx, and similarly, we can use trigonometric properties to describe Vy equals sine theta, sorry, Vy initial, because remember our velocity is changing, equals sine theta Vi. And you can try it yourself. The triangle works. This isn't going to be the case all the time. Sometimes, once we get to dynamics and talk about forces on an incline and things like that, it will it can be different depending on the circumstance. But essentially, these are our equations to describe the velocity in the x direction and the y direction um, for in, in terms of initial velocity at an angle. Pause the video if it and do a little check in your mind. Does this make sense? Do you follow with me so far? If you don't, go ahead and rewatch the video and rewind. Um, and yeah. So from here, what we can do is we can use these equations and plug them into our kinematic equations. So we have our VIY right here, and we can use this equation that we have in terms of our givens. Now, our givens are our values that have numbers. We can say our maybe our initial velocity is something like, um, let's say 2 meters per second. And we can use this and plug in real values to get what we want. And it's kind of beautiful how this works out, how we can take these random and weird concepts and plug them into equations that work. So let's write our equation in terms of our givens that we already have. Negative h equals, um, let's see, sine theta vi. Sine theta vi. That's our y component of the initial velocity. T times the letter t, which is time, plus 1/2 gt squared. Now, in this instance, we are trying to solve for t. So we are going to, we can do some algebra and some equation manipulation in order to solve for t. So let's do this. We have negative h equals, let's factor out the t, and then we have sine theta vi plus 1/2 gt. So this is the part that's interesting because we want to essentially solve this equation and make it so that it's manageable and that we have an understanding for t. Now, one of these two factors will give us something negative. Using our knowledge of algebra, we can figure out that one of these two terms has to be negative in order for it to make sense in terms of the height. Now, t right here by itself, it would be kind of strange to think about negative time, right? That wouldn't really make a lot of sense. If we go over to this term right here, our g, remember, is negative. And so it makes sense for this term here to be negative. So what we can do is some hand wavy math and essentially set negative h equal to sine theta vi plus 1/2 gt. Now, essentially, what we can do is we can move the equation around, manipulate it, and we eventually get t equals negative h minus sine theta vi, and we multiply by the 2 for the 1/2 all over g. And we can simplify this because we know that g is actually negative. We can make all of this positive, and we end up getting t equals 2h plus sine theta plus 2 sine theta, excuse me. That would have been disastrous if I forgot the 2. 2 sine theta over g. And now because g is in the, um, because we already used the negative on the g to cancel everything out, we can just use the absolute value of g. Hopefully this makes sense, and this is clicking so far. All we did is we set up an equation where a kinematic equation where we could find the time. Now that's going to be our answer to the first one. Yippee, we did it. We're halfway there. But how are we going to find the final velocity? This is where things get a little bit trickier. So let's go out and talk about the x direction. We haven't been doing a lot of talking about the x direction. Since there's no acceleration in the x direction, velocity is going to be constant. So we have this lovely equation, v, and in this case, we're talking about the x velocity, vx equals dt, or distance over time. Well, we found here that vx is cosine theta vi, so we can write it like this. Cosine theta vi equals dx times t. Now, the t was previously unknown, but if we plug in the values that were given, we can find time and multiply it by our unknown, which is our distance, in order to get cosine theta vi. And we can use some algebraic multiplication, excuse me, division, to solve for dx. It could be in another question that they ask you for the distance traveled. Um, and that would simply be cosine theta vi divided by t. That's our equation for our distance. That's what they could ask you. Now, this last part, the final velocity, is the hardest part to find. We found our velocity in the x direction. We found our final velocity. Um, it's the same thing essentially as our in the x direction. Velocity is constant. Final velocity in the x direction is the same thing as the final velocity in the um, is the same thing as our initial velocity in the x direction. Doesn't change. It's constant. It's not going anywhere unless we have air resistance. But at most basic level university and high school courses, they're not going to care about air resistance. Um, so how can we find our VI, our, excuse me, our final velocity? What we can do is, first of all, we need to find the final y velocity. Our final x velocity is just going to be our Vx, which is this equation down here that we already derived. So we need to find our V final in the y direction. So if you remember, we can use our kinematics equations, plus 1/2 a t squared. And in this instance, we're going to substitute our knowns. Our acceleration is our negative g, or negative 9.81. Our final velocity in the y direction, is what we're solving for. We can plug in our known, which is VIY. We got it over here, which is sine theta VI. Sine theta VI. Um, then we have, oh, excuse me, I totally messed this up. It is not 1/2 AT squared. I was thinking in terms of distance. Wrong equation. It is 2 times the distance. Or no, it is not 2 times the distance. It's just acceleration times time. Wow, I'm a little tired here. Okay, acceleration times time. That would have been pretty bad if I forgot about that. So this is our equation. We're usually given on on tests. You're usually given these kinematic equations, so you don't have to memorize them or think about them too much. They're usually right there, and if not, they're super easy to derive and logic through. Um, and yeah, so our acceleration is going to be negative g. Um, our time is going to be this ugly thing that we got here, which is um, 2h plus 2 sine theta over g. Now, if you look, these g's cancel, which tells us something about the equation. The acceleration due to the force of gravity doesn't matter. So on different planets, when they have different acceleration due to gravity, if we did the same thing, we'd find the same principles. We'd find the same velocity. If we did this experiment on Mars or Jupiter or Pluto or wherever, and we had the same, we assumed the same, no air resistance, no friction or anything like that, we'd still get the same results. So our VFY is equal to sine theta. Because this simplifies, we actually get, we add this part over here. So we get 3 sine theta. Oh, wait, nope. Oops, we cannot add those terms together because we have the VI right here. I was about to teach some false doctrine. Sine theta VI minus 2H minus 2 sine theta. That's our VFY in the Y direction. Cool. So we have our final velocity, but what's going on? We have our final velocity in the Y direction. Sorry, excuse me, in the X direction, which is our constant, Vx, and then we have Vfy, our final Y direction velocity. Then how do we go about calculating Vf? We just use our basic Pythagorean theorem, right? A squared plus B squared equals C squared. So Vx squared plus Vfy squared equals Vf. Beautiful. And essentially we can take these terms, we square this term right here, and then we also square this term right here. And then we put both of those into our equation, take the square root, and it's smooth sailing from there. I hope this helped do kinematics. I know it can be a little tricky at an angle, but if you boil it down into 2 separate components and do the right math and make sure you have the right equations, it's actually not too bad. Hope this helps. Hope you have a good one and keep on crushing it. Have a good one.